So now we are moving on to our first speaker, invited speaker. I would like to invite Professor Akyildiz to take the stage, please. Let's applaud him, please. Professor Ian is from Georgia Institute of Technology. He has received his bachelor and master degree and PhD degree in electrical computer engineer from University of Erlangen in Nuremberg. He is a life fellow from IEEE, and since fall 2020, he has been a distinguished professor and the founder director of the Center for Robotics and Wireless Communication in Challenging Environments at the University of Iceland. He's also the founder and the editor-in-chief of the ITU Journal on Future and Evolved Technologies since 2020, and he serves as advisory board and Technology Innovation Institute in Abu Dhabi. He founded the Truth Incorporation, a Georgia-based consulting firm, in '89, and from '85 to 2020, he held the King Byers Chair Professorship at Georgia Tech, where he also directed the Broadband Wireless Network Laboratory. Between 2017 and 2020, he led the Wireless Network Laboratory through a Russian Mega Grant Award. IEEE Fellow and the ICM Fellow, he has received the major recognitions, including the Humboldt Research Award at the Tumbetak Award, and as of October 2005, he holds an 8 index of 145 with over 155,000 citations. His current research interest spans AI native networks, Network 2030, the metaverse, XR communications, 6G, 7G systems, terahertz communications, and on the other networks. His talk is going to have the title of the Cognitive Wireless Area, AI and ML as Engine of Next Generation Communication Networks. Professor Ian, be my guest. Yes. Thank you. The floor is yours.
On? Yes, now. Good morning. Thanks a lot, Luciano, for a nice introduction. And also thanks to organizers for inviting me here. After 22 years, I'm back. And I hope I will not wait another 22 years. Maybe I will not be alive to come back here. So last time we had like 250 people. I remember that. So many students that time. So the title of the talk is The Cognitive Wireless Era, AI and Machine Learning as the Engine of Next Generation Communication Networks. And where do I go? This way? It's not working. This way? Here? Oh, perfect. So, sorry. So we are moving from reactive to cognitive networks. Luciana tried to explain all these things before, but so this is my view of 4G was more connecting people, 5G connecting things like Internet of Things era, and now in 6G we are talking about connecting intelligence and also self-healing and self-predicting networks. In other words, zero-touch network management type. Everything is automated networks. And AI is not a tool, but the fundamental fabric of this new cognitive network. And cognitive era will transform society, healthcare, and industry, and our relationship with technology. So let me explain you more about this transformation. I fixed that, but it was too late. Not transition, transformation. So the economic impact, we're expecting like trillions in global GDP, and societal impact, like remote surgery. Somebody sitting in Rio de Janeiro can have surgery here in Santa Rita, for example. You can imagine how important real-time latency becomes. Autonomous transportation, autonomous cars and all that, disaster response, environmental monitoring, and geopolitical impact. Leadership in 6G is leadership of the future digital economy. So these are crucial points for this transformation to this cognitive era. So another view is, I hope I send you the right slides now. So global network 3D coverage. So this is also called Tower of Babel. You see many network paradigms, starting from the underwater communication networks to terrestrial networks, all types of like 4G, 5G, whatever you can think of on the Wi-Fi terrestrial, and aerial networks like drones and LEOs, MEOs, and geosatellite networks, and then also like space network, like deep space and space networks, as I mentioned to you, LEOs, MEOs, and GEOs, and unmanned air vehicles for the aerial network. So this is the kind of like 3D coverage. That means the objective is seamless integration of all these existing networks. That will be a challenge. I will come back to it, how we will realize this. So this networking 2030 to 2040, there is a ITU group. I also have a position there, International Telecommunication Union. There is a group, they came up with similar slides, but I slightly changed it, what I like. So we have all these applications from telepresence, healthcare, education, automotive industry, entertainment, industrial automation, and all these underlying use cases. And they are sitting on the network, which is the 6G and beyond systems, and all the paradigms I showed you, these Tower of Babel, and kind of like 3D networking. And the fundamental or the denominator of all these technologies will be AI and machine learning. And of course, security, privacy, and safety are very important in this big picture. And let me also give you this contrast from 5G to 6G. So there are a couple KPIs. For example, the peak spectral efficiency in 5G systems from 30 bits per second per hertz will go to 60 bits per seconds per hertz for the 6G systems. And in 5G, we have peak data rates like 30 gigabit per second. And in 6G, we are talking about like terabit per second speeds, data rates. And reliability will jump from 10 to the minus 5 to 10 to the minus 9. And another very important QS parameter is the end-to-end latency. In 5G, we were hoping to reach 1 millisecond, but it's really still a dream, because we are happy if you can get 15 millisecond end-to-end latencies in 5G. And for 6G, we are talking about like 0.1 millisecond or almost non-zero latency, like kind of like quantum communications directions, right? So it's kind of like ultra low latency systems. And then the mobility will jump from 500 kilometer per hour to 1,000 plus kilometer per hour. And the cell edge data rate will be from 0.1 gigabit per second to 1 gigabit per second. But I have to mention this, cell edge is, I hope you know what that means, that you are too far from the base station. And so the coverage, the data rates are lower accordingly because of the cell towers distance to the users. But the cell edge issue becomes obsolete in the 5G, especially 5G and beyond 6G, because everything is dictated by the software-defined networking controllers. And there will be no issue of these fixed cells, but there will be dynamic cells. Okay, the controllers will create these dynamic cells, kind of like virtual cells, and then the user will be locked into the best serving tower or base station. Accordingly, the cell edge problem will diminish in real 5G and of course in 6G. So these are the directions in 6G, plus of course massive device connectivity and seamless the architecture I showed you, 3D space, terrestrial, and underwater integrations are the objectives for the 6G. And so this is the paper that I wrote with my last two PhD students at Georgia Tech. So we showed some key technologies for 6G and beyond. I slightly changed it because of the technology progress. This was done back in 2018 and published 2020. So what are the 6G directions? Of course, terrorist band communication. I will also mention that later on. I work on it since 20 years. And new network architectures, most AI native architectures we are talking about. And zero-touch network management, meaning automated network management. No humans will be involved in that. And Internet of Space things like satellites, all types of satellites, CubeSats, and unmanned air vehicles. And the semantic communication. Again, I will mention some of these in later slides. Then underwater communication is also very, very important, not only for military, but also for civilian applications. And so these are most, and intelligent surfaces. Again, Luciana mentioned this. And I also worked on it like almost 10 years. We started in 2011. Now to people woke up in the last 3 years, everybody talk about intelligent surfaces or meta surfaces. I will also point that out later on. So these are all 6G. And so metaverse is very, very important. So I put it in the 6.5G. Metaverse is the integration of the physical world and the virtual world. Seamless integration. So you will not see, is it really a virtual world or is it a physical world? That's the objective that we are working on, also many people. And I'm talking about like extended reality and holographic type communication, and also multimedia, meaning multi-sensory data, not only like three, like the voice, data, and image, but you will also add all these human senses, right? Like, smelling, hearing, touching, even emotional sensing. So that's the way it goes to the metaverse. And people are using also this word immersive communication. Also, some people are using digital twins, but digital twins are not exactly the metaverse, because these are all like more, intelligently developed simulation models. So, but it's kind of like underneath of metaverse. And Ericsson is working on this under the project called Internet of Senses. And this is like mostly 6.5G. And 7G are, I work on all these except quantum the last 20 years. Internet of nanoscale machines, very, very small machines that you can use in many, many use cases. And Internet of bio-nanoscale machines, this is mostly for health cases, and also brain-computer interfaces. In fact, these mRNA, which is the vaccine for COVID, this is part of these bio-nanothings concepts. And then quantum communication is also important. Unfortunately, since 30 years, we are saying quantum computing and quantum communications is up and coming, and it's very, very difficult. So they have some very good progress in cryptography, but in actual communications, there are some projects in Europe and the US, but they are really toy examples, in my opinion. We have some years to go. So the future wireless systems vision, we have these three biggest challenges or pillars, you can imagine that. So like extreme density, we will have 10 to the power 7 devices per square kilometer. So the problem becomes scalability. Then I talked about the latency, end-to-end latency, like near zero latency we are talking about, and ultra high speed. In other words, terabit per second. So to have all these objectives, we have a bunch of these applications, and I mentioned before, and they are also here again. So all these use cases need these performance results, and we are hoping that AI and machine learning will help us to achieve these objectives in terms of these performance metrics. So let's go to this AI, because that will be the denominator of our future communications and computing. So I'm sure you know all of these. So AI is the big arch. So human intelligence exited by machines. Then we have underneath machine learning. We have a bunch of algorithms that learn from data and experience and keep learning, and they are trying to perfectize the outputs. Then we have these neural networks, which are the subset of these machine learning techniques. They are most inspired by biology, like the neurons, like humans, neurons. And they are organized in layers, as you see here, that you have inputs here on the left side. And then there's this hidden layer, like here, one layer. and the output. So I always made a joke when I was starting teaching it 10 years ago in the class, like it's making sausage, meaning you put some stuff in, you don't know what's happening in the hidden layer, you get something out, right? So this is the problem of the explainability of AI, which I will point out again. We don't know exactly what the hell is happening inside, right? So anyhow, we'll continue that. So then there are these deep learning. They are mostly like multi-layered neural networks that you see instead of one layer, we have multiple layers, and then inputs and outputs, right? And then generative AI, these are creating synthetic data. We really need synthetic data because the more data we have, the more reliable our machine learning algorithms become. And we cannot collect 50 years of data, so we can also create so-called synthetic data. So then we have this generative AI concept. So these are a collection of algorithms, machine learning algorithms that can generate human-like content. So that's the connection between all these terminologies that I'm sure you heard about all of these. So now let's go back to this big picture. So what I'm pointing out in this talk is, I showed you this before. There are many, many papers already on the market or in the literature. So they keep writing papers in all these areas. But what I'm trying to point out is now we should start to think about AI and machine learning and then somehow incorporate that or use it as a base to revisit all of these. So that's the point I will try to make in this talk. So now I'm not saying that we will reinvent everything, but we will base everything to AI machine learning as I showed as denominator, right? So let's talk about the first case, because I mentioned this in the top, on the top, AI native networking architectures, right? So why do we need that? First of all, we need a paradigm shift. That's what I mentioned to you before. So the old school, that's the way we are doing this. So we have a lot of papers. They're always struggling with scalability, nonlinearity in the channels, non-stationary problems, partial observability, and real-time constraints. And then also we have fixed rules, and mostly we are doing manual tuning, meaning we input certain parameters. And when we look at these future networks, we have a lot of dynamic behavior, large scale, orders of magnitude more complex, very fast, and highly unpredictable networking. So that's why we need these AI-based, AI-native solutions. So now what I'm trying to show you is also there are papers on the market. They're always adding on the AI solutions. That's not what I'm talking about. We need to start from AI and build up on these new protocols, for example, right? NUFI, MAC, and the networking layers, and maybe also transport layers. And then we also try to understand these real-time adaptation problems. How do we handle massive data? And then also the devices should make autonomous decisions because we are injecting more and more intelligence to them, right? And so then we will come up with networks which are much more intelligent, more efficient, and more secure. So now the objective is, again, adaptability, speed, intelligence, making future networks smarter, greener, energy, and more secure. So let's start with the PHY layer, right? So the channel estimation is a problem since maybe, I don't know, 100 years. Everybody is working on new channel models for megahertz, terahertz, gigahertz, whatever. So now what we are saying is let's try to revisit everything and use these channel estimation by using these convolutional neural networks or recurrent neural networks like long short-term memory method or transfer models. So now we have this case that, as you see here, so what we are saying is we have all these channel features, receive signal strengths, and signal to noise ratio, delay spread, all of these inputs. So we give to these machine learning algorithms, convolution layers, pooling layers, and then we come up with these much more accurate estimated channel parameters or channel behavior. So that's the way that we should try revisit all of these channel models. And another thing here is the time series signal processing. Can we use these hybrid concurrent neural networks and recurrent neural network models as a hybrid? So you see here input time series. Oops, sorry. Input time series. So we have a convolutional layers and pooling and bunch of convolutional layers, and then we come up with this fully connected layer at the end to create these time series single processing solutions. I really send you something. I have so many versions of this talk. So anyhow, so let's talk about the semantic communications. In the classes, we learn always the syntactic case, like error control. Before I fall down, error control, like you have FECs for error correction or ARQs, and mostly we check ones and zeros that are correct or not. But now things are changing because we are using many machines. They don't understand the context. So we need to somehow inject the context of this communication purposes. That's why we talk about the semantic communications. AI can extract meaning rather than just bits. So I will come back to this again when I talk about challenges there for the semantic communications. Then more like spectrum is always a problem. Like, cognitive radio networks like dynamic spectrum access. Actually, Luciano also mentioned in their 6G program. So that's another problem, that we may use AI-based solutions, right? For example, we can do this deep learning-based spectrum sensing and sharing. I worked also 20 years on cognitive radio networks. So we use all this spectrum sensing and sharing, but there was no AI or machine learning solutions there. So we need to revisit those spectrum sensing and sharing cases and then come up with interesting solutions like I show you here. So a bunch of these cases, right? So we have all this spectrum available from the spectrum map, and then we somehow model with the machine learning algorithm, and then accordingly, intelligently assign the spectrums dynamically to whatever bandwidth is needed to these users, for example. And also, energy is always a problem. So we can also use power-aware machine learning algorithms, because one of the disadvantages of these algorithms is they need a lot of memory space, and also they eat a lot of energy. So I will come back to that too. So these are issues, but there are also some challenges that we need to solve. And so then also the problem is we do not have enough data. So these algorithms are extremely data hungry. So now, for example, we are developing all the 6G solutions. There is no 6G existing. Now we need to create some synthetic data, right? So now, can we create these AI-generated wireless signals, like using generative adversarial networks, that they can create synthetic but realistic channel data, and use those data to use our machine learning algorithms to come up with much more efficient and valid results. Then here is, again, everybody works on MIMOs since like at least a decade. And so can we use now like recurrent neural networks or reinforcement learning or federated learning to optimize these beamforms and beam management? That's a topic that people wrote papers and still writing, but we should really revisit that again, starting from these bottom up, from AI and machine learning, come up with new solutions. Please don't do add-on. So people are trying to do that. That's not the way to do it, right? So we have to reset our minds and come up with these new AI machine learning based solutions. So let's go back to the MAC layer. I hope I'm not boring you with all these things. Like, for example, MAC protocols. There are thousands of MAC protocols on the market because it's the easiest research that you just tweak here and there. And mostly you make some assumptions like window size or whatever, or frame size, all of these things, right? So can we use, again, kind of like reinforcement learning for self-optimizing contention window of decision, for example, when you use like CSMA, CA, or some, random-based access schemes as an example. And then back off, like, it backs off based on some algorithms, as you know, but can we use machine learning algorithms that they do it by themselves, right? Without putting some parameters there, right? And link quality and prediction and adaptation. I mentioned to you about channel, but this is on the Mac layer. Then scheduling is always a problem. There are many scheduling algorithms. And can we come up with new scheduling algorithms? For example, transformers-based scheduling. And instead of getting, using heuristic schedulers. And can we use multi-agent reinforcement learning algorithms for distributed cooperative resource allocation among base stations, drones, and user devices, and cooperative interference management? Then mobility management is a problem, as you know, handovers and handover predictions. And so then I make suggestions, right? We can use RNNs, recurrent neural networks, or generative neural networks, or hybrid of them, and come up with new mobility management schemes. And all these other things are common problems, right? Scheduling, resource allocation, I mentioned before, handover optimization, hybrid ARQ power control. Again, we can maybe use deep reinforcement learning to come up with new solutions, right? And and then we have these multiple KPIs, kind of like joint optimizing these KPIs. Again, we may need some algorithms like reinforcement learning to help us to achieve these joint optimization on the Mac level. And routing layer is also a problem. We have many routing algorithms. Some of them are heuristic algorithms, but many versions of that. So now, can we come up with like deep reinforcement learning for adaptive routing? Plus, the interesting thing will be here is that not only the algorithm, but also the nodes themselves decide intelligently where to reroute it, right? So that's the beauty of the intelligence built into these devices. And then they can always try to dynamically reach optimal path. Then federated learning. So it's kind of like you see here a bunch of UAVs flying, and they can use their federated learning each locally. And then they can put it to leader drone. And the leader drone can create this global model. But in this case, we can also achieve security because all these local federated learning models, they don't need to send everything, these results here, right? Only certain input. And this federated learning can somehow figure out what all these local ones are trying to achieve. So that's one of the beauties of the federated learning, to achieve security and keep that locally. And so then graph neural networks, we can see we can model network topology as a matrix, and then it can help us to achieve all this optimal path using some new routing algorithms. And so I gave you some examples for the protocol layers, but there are some more problems actually, so-called scalability problem. So can we build AI which is fast and efficient enough for the real world? Because they're really very cumbersome, very large models, right? So it talks about like ChatGPT, for example, right? So if you run these complex AI models on resource-constrained device like sensors, good luck, right? So like, as an example, ultra-reliable, low latency, URLLC, actually, there's a typo here. And so it's almost impossible with the current technology. So can we use some edge computing with lightweight models, or go to the neuromorphic computing, for example, that may help us to address this real-time and resource-constrained problem? Then data scarcity and generalization. So as I mentioned, I keep mentioning it, so they need a lot of data to get accurate results. And can we use, these are also on the market, people are trying to do transfer learning, meta learning, and synthetic data generation. So in other words, trying to reduce or distill the data to input so that you need less data for your AI models. And energy efficiency, and as we said, that these are very large data sets, and to process them you need a lot of energy, and especially like transformers. So we need green AI, right? So can we develop some sparsity-aware neural networks for energy-efficient inference? And we should also think about hardware-aware AIs. So can we co-design like hardware and software? Software is the part of AI's co-design of algorithms and specialized hardware for efficiency. The next problem is the trust problem. Can we trust the decisions these AI systems make? So I mentioned this in one of these talks like 2 months ago. And unfortunately, AI is not a science. And so some people attack me, of course, as usual. AI is not a science because you don't have theorems and proofs. You don't totally rely on the results, right? Because it's all probabilistic. So we try to reach like 99.9% valid, but that's you cannot say like 100%. This is the result, theorem and proof. So the issue here is we need to kind of like achieve this explainable AI or XAI. So kind of like I told you about this black box, like these internal things, all these layers. You don't know what the hell is going on there. So we need to find out some ways of finding out what the hell is going inside, right? And so can we use hybrid symbolic neural approach for greater transparency of these hidden layers, right? And then trustworthy AI for security and robustness, protecting machine learning systems against adversarial attacks, and also support interoperability or beamforming and resource allocation. And of course, ethics and fairness is a big issue in all these AI communities. How we can achieve these bias and fairness and all these issues. That's a subject. It's not for engineers, but it's an overall sociology problem. And privacy, right? So for privacy, people are talking about federated learning and differential privacy. So these are also objectives for the trust issue. The third leg is the integration problem. So how can we integrate these new technology into our existing world, right? So for example, lack of information theory. So as I told you, we need kind of like towards the science of AI, not just heuristics, right? So how can we come up with, it's not easy, by the way, information theory framework for AI solutions, for example? Or can we also go, because now we are exhausting all these single AI solutions, and now it's time to do more and more hybrid AI solutions, right? Using each technique's pros and then combining them. And hybrid environments that we can use these three Tower of Babel case with all from underwater all the way to the satellites. How can we seamlessly integrate all these existing networks and address the scalability and adaptation problems, for example? Foundation models, large language models, pre-trained on massive multimodal network data. And these are also very large models, right? They need a lot of space and a lot of processing time. There is also these small language models. So there's a lot of activity going on there. But also, how can we integrate these new AI-based networking with legacy systems? We cannot say we do have all of this, but then we have all these other ones. They will drag the new techniques, new networks slower and with more cumbersome solutions, right? So that's a coexistence problem. And of course, this is the standardization, regularization, interoperability. That is a part of the ITU as a group of working on these for these 6G and beyond systems and using AI machine learning. And so that's the overall native AI native networking. So let's go back to those clouds that I showed you, terahertz band. I started terahertz band communication back in 2006. So I was interested in this nanotechnology. And then with the nanotechnology, I came to the nanosensors. From nanosensors, I came to the graphene materials. From graphene materials, I came to the terahertz band. That was my way to the terahertz band. So we wrote this, I had so many, I will show you so many results, papers and all that. And so this one, we were invited to give another paper, June 2022. So that got the best paper award. I'm going to Taiwan not for only that, by the way. So we got the best paper award for this last 22 paper. But this is kind of like collection of all papers that we did the last 15 years. These are all my former students, by the way. Han and Shoaini and all that. Journey is now the top-notch guy in terahertz. Is continuing that. So, 6G requirements, minimum end-to-end latency, very high reliability, very high data rates, and the wireless data traffic is exponentially growing. And we have multi-billion fixed devices, and wireless data rates are doubling every 18 months. So we need terabit per second links, especially in 6G. So then we ended up in this high frequencies, right? And in fact, when I had this 15 years ago, there's no man's land was here in terahertz band, So now I push this to the petahertz, no man's land, petahertz. So current focus, everybody's working on terahertz band now. So as you see here, I had 60 people working on it in many countries, from USA, Army, NSF, and in Finland, Finnish distinguished professor, Catalonia, in Barcelona, I started a center there, still existing, Humboldt Award in Germany, and in Saudi Arabia, even, and many others. 60 people worked on all these terahertz issues. Nothing AI, by the way, here in this case. I'm just showing you what we did, like from nano transceivers, antennas, channel models, and communication solutions, and etc. So we developed these plasmonic nano antenna. We got patents for them, and also transceiver. It's kind of like front end. Both patents are existing. And then we had this problem of distance. In the terahertz band, when you put transmitter and receiver more than 1 meter, the signals fade because of the water particles in the channel. And then you cannot go beyond 1 meter. So we worked on it like 10 years to solve this grand challenge problem of distance. So one of them was ultramassive MIMO. Now it's part of 6G when you read it. So they say ultramassive MIMO. And we got a patent on this. We have 1024 by 1024 elements in these, nanoscale antennas, plasmonic nano antenna, which is sitting on a graphene-based material. And so that was the challenge to solve the distance problem. Another solution was in 2011. I was giving a talk about this problem in Cyprus, and some of these people were in the talk. So they said, look, they have this idea about surfaces, and we should 2011. People woke up like 3 years ago. So we start to work, and we wrote a FET project, EU Future Evolving Technologies project. Success rate in Brussels is like 3%. The project's name was Snow White. We got busted, meaning rejected. Then second time, next year, again rejected. So we said we should rebrand it, change the name to Wiser Surf. So that's this thing here, wisersurf.eu. From 2016 to 2021, we were like 40 professors, but clearly interdisciplinary, like 4th research center in Greece, Crete, and University of Cyprus, Catalonia, Barcelona, Aalto. You can find from computer science, antenna people, algorithm people, physics people, material people, everybody was there. So we developed this, and also the Fraunhofer Institute in Berlin, they did the fabrication. You can see this fabrication thing. This was like 2017, 18. So we got a patent, and there's no time to tell all of this here. So, and then please revisit this website. There are tons of information there, but now we are out. So now people came in and they're writing papers. So, so now what we need, so we are going back to the AI native issues, right? For the terahertz band, channel is a problem, right? So how can we channel estimate and also beam alignment, right? So we can have some solutions. In fact, anyhow, so I changed some stuff here. Anyhow. So so some solutions here. We can use concurrent neural networks, extract special features from terahertz channel measurements. And then we can, that's the hybrid part. We can use vision transformers, handling sparse terahertz channel matrices efficiently. Reinforcement learning, like we can use this deep deterministic policy gradient gradient, optimized beam alignment in real time, and hierarchical reinforcement learning for multi-stage beam search for fast initial access. And federated learning, we can use these distributed terrorist channel learning across multiple base stations without sharing raw data, taking care of the security problems. And as I told you, terrorist channel is a big problem because of these high path losses. That's why we have distance problem, right? So maybe these algorithms can help us to estimate the channels much better and maybe come up with better solutions and better beamforming algorithms, right? Another issue is resource allocation and spectrum management. And I mentioned some of them before, but so because of the terrorist band peculiarities, we may come up with new algorithms like multi-agent reinforcement learning, such as multi-agent deep deterministic policy gradient for dynamic power and subband allocations, graph neural networks, and meta learning, like how can we learn how to learn, so they may help us. And so overcoming molecular absorption and blockage. And there are some solutions that you can see here: physics-informed neural networks, generative AI diffusion models and GANs, and Bayesian deep learning. And so ultramassive MIMO and reconfigurable intelligence surfaces. Again, I have to mention that that project, we did not have anything AI there. So maybe we can have transformer-based beamforming. And for optimization of these surfaces, we can use dynamic reinforcement or deep reinforcement learnings. And so also deep unfolding, deep learning, and also optimization, kind of like using iterative algorithms, orthogonal matching pursuit, etc. So these algorithms can help us. And localization and sensing, these are interesting. There are these solutions called few shot learning. Instead of getting a lot of data, you have like samples, like one sample or 5 samples, or you create, they are called Siamese neural networks. You create a twin of these network, and that's called Siamese, but then with less activities there, and you play with these Siamese neural network. And so then, meaning this can help us with working with limited training data and come up with accurate solutions. And time series transformers, like how can we process these terahertz radar signals for high resolution sensing. So there are more directions, like federated learning for distributed systems, quantum machine learning for terahertz signal processing, and this is also very important, neuromorphic computing for low latency terahertz beam tracking. So let's go to the semantic case. So I mentioned to you before, we learned always in the classrooms, what is received is equal what is sent. We always checked ones and zeros, as you see here on the left-hand side. And then we realized that if everything was correctly received, we said everything is correct. But now we understand, we need to understand the semantic, the meaning of the data. So is it what is received is equal what is meant to send? So when you send something hot, so what are you talking about? Are you talking about the weather? Are you talking about the soup? Are you talking about the temperature? Whatever, right? So that's why we need to understand the context about semantic of this communication, right? Like, for example, like pedestrian 10 meters ahead crossing left to right. So we need to only transmit only that information, the semantic meaning, so that we can save the massive bandwidth and latency problems. And so this goes back to many, many years. You see Claude Shannon and Warren Weaver. So back in 1953, Warren Weaver and also with Claude Shannon, they wrote these papers, 48, 49, and also 53. So the one that we know is Shannon's theory, mathematical theory. That's the one syntactic technical problem. How accurately can the symbols of communication be transmitted? That's literally that's what he said, meaning ones and zeros are correctly received. And then the semantic problem is how precisely the transmitted symbols convey the desired meaning. And then effectiveness problem, how effective is this communication, right? So what do we do for this semantic information extraction and understanding? Since COVID, there are hundreds of papers on semantic communication. In the 80s, when you ask people, what do? They said, high-speed networks. And then 90s, they said ATM networks. And then in 2000s, they start to say, we're doing sensor networks. So now the last 5 years, like surfaces, terahertz, and semantic communication. So how do we extract semantic information, right? Natural language processing. Some people work with the speech processing people. They can decode human intent in text and speech. Computer vision, with vision people, signal processing. They can extract high-level features like objects, actions from images and videos. And so these are the possible solutions that are using, right? And knowledge graphs and ontology structures, semantic relationships for efficient reasoning. So as I told you, there are tons of, hundreds of papers on the market. So what we say is with the AI, we can say context-aware transmission and compression. Like AI models, transformers, deep neural networks, they can identify and transmit only task-relevant information. As I mentioned to you about like 10 meters ahead, the pedestrian is walking on the street, for example, right? So just that simple, relevant information. Semantic compression reduces data overhead by discarding many irrelevant details and like background noises in speech and others. So what can we do with AIs, right? So I'm giving you some ideas here, directions. Adaptive resource allocation with the objective of semantic communication, right? For example, reinforcement learning can optimize bandwidth, power, and latency based on semantic importance. We can classify, how important that information is. That information is kind of like relevancy, right? And then we can prioritize them, and accordingly we can discard them. Or semantic channel coding error correction. Neural decoders recover meaning even with errors. And edge AI for distributed semantic processing. So we can use federated learning, collaborative semantic understanding without raw data sharing. And we can have these tiny machine learning algorithms to allow lightweight models for the sensors and Internet of Things, which make it easy to use. And I mentioned to you before an AI native case, so I'm just repeating that again. Interpretability and trust, like explainable AI concept is again reappearing, right? And also the black box AI, understanding what's happening in these hidden layers, right? And standardization and semantic frameworks, computational overhead, privacy and security risks, and dynamic in certain environments. So these are, again, taking the semantic part as the objective and trying to solve these problems. So there are more to say, but I jumped to the zero-touch network management. So the basic idea is self-configuring, self-optimizing, self-healing networks with minimal or no human intervention. So my personal opinion is I will never trust this for the future. So only certain parts can be automatized, but not fully automatized. So, but people are working on this. All these big companies from Ericsson to Nokia, zero-touch network management issue, right? So because with human intervening, so it's very, very difficult. We have billions of devices, and we have all these metrics like ultra low latency, reliability, etc., zettabytes data, and energy consumption. And also when the humans intervene, they cause delays. It injects the latency, and also sometimes errors can be made by the humans. So that's why we want to go to these AI, intelligent-based network management, autonomous network management. So that's the objective. And so like here you see with the human loop here, in the future we try to get everything to the AI orchestrator. That means a brain which will handle all of these automatically. But as I said before, many networks I will not totally trust totally AI based solution. Partly maybe zero-touch network management may be realistic in this case. And so I deleted this, but it's still here. Wow. So what are the things that we can use for key technologies? For dynamic and real-time optimization, we may use deep reinforcement learning. For privacy preserving and collaborative AI, we may use federated learning. and to simulate and test networks using synthetic data, digital twins, and generative AI, and to build trust and ensure decisions support transparently. We can use explainable XI solutions. And so grand challenges to path to autonomy, data problem. How do we train AI without real 6G data? Okay. Can we use digital twins and federated learning? Trust problem. How do we trust a black box AI? Speed problem. How can I make decisions in under 1 millisecond? Lightweight edge AI can be used. And unity problem. How can I manage a mix of satellites, drones, and ground systems? In other words, cross-domain AI orchestration. So now I come to the last part. I hope I'm not boring you with all these things. So this is the issue, as I was talking about, seamlessly connecting all these networks from deep seas all the way to the deep space. So like, think about the following case: a single packet moving from an underwater sensor to a drone, to a satellite, to a terrestrial base station, with an AI orchestrator managing the entire complex handover in real time. So that's the cognitive wireless era I'm talking about. So what I did so far is I talked all these separately. Now I'm trying to converge everything to these type of network, right? So so what are the challenges? When you look, I'm sure you know all these things, that each of them has different characteristics. Like underwater communication uses mainly acoustic communication, right? Part a little bit optical. And in the terrestrial, we are heavily using electromagnetics, some optical, and aerial networks also electromagnetic. So and then also they all have different protocols, different channels, right? And the underwater are working around kilobit per second, and in the terrestrial network we are talking about like terabit per second levels, and in the drones we are still talking about like maybe gigahertz levels. So there are all these, mismatch of these network characteristics that we are talking about. So how do we solve this problem seamless, right? So that's why we say, remember I told you we need AI-based solutions, protocols, etc. Now we also need to consider this one, that we can have these easy protocol translations between all these mismatching network paradigms, right? And and also the challenge is no universal standards for AI-driven multi-domain networking is existing, but it will come soon. So the AI orchestrator, the brain, will take care of all of this, right? So that's the way we will go, network management. Centralized intelligence, then also use distributed agents, and federated learning is always looking at, security aspects and keeping the raw data inside locally, but only certain parts are shared. And this synchronization will be very hard, difficult problem to solve in these different network paradigms. And automated network management, we are dealing still with 6G network management, zero-touch network management. Now, if you have all of these together, that will be a hell of a challenge you can imagine, right? And AI-driven resource allocation, they are again popping up, but in this case, again, with these different paradigms, like dynamic spectrum sharing. But in this case, we have many networks in front of us, and how we will share the, for example, spectrums between all these different network paradigms, and how do we do load balancing of this traffic, for example, and also energy efficient operation. And of course, we'll go mostly to this network slicing, which we started with 5G, and it will still continue that. So, like for example, we may have slices based on mission critical operations like defense cases, or industrial automation, smart factories, remote environmental monitoring. So these are kind of like definition of slices that we can slice the traffic and accordingly take care of them and dynamically allocate resources to these slices. But again, these slices will be from all these different types of networks, right? So that will be really challenging again. And how do we handle the slices, life cycles of the slices? And how can we guarantee isolation between slices, for example, between military and civilian applications, and security and privacy in multi-domain networks. Underwater sensors can easily be tampered with. Satellite links are susceptible to jamming, and terrestrial end nodes are physical attacks. So again, we need some solutions for there. And energy efficiency, again, we need to solve those. And handover becomes a very challenging problem. You know, how do we hand over from one network to another, not only within one intra-network, but all these different internet networks, network paradigms, and how we do it efficiently. So the last one is, I really burned your engines. Maybe some people got bored, or what can I do? So the cognitive era is here. And so we are standing really at the edge. We are just starting it. And so shifting from connecting things to connecting intelligence, from reactive networks, we are moving to predictive to cognitive systems. And AI native is the engine, meaning I always use the word denominator. So everything will be founded on that one. And we will have a transformation of society, industry, and human potential. And how long is the problem, right? And so the question is how we can work together. And instead of writing all these epsilon papers, you know, that's the problem with still, since 45 years I'm in this business, many super brains are misused. They are taking one algorithm, Professor Carl's, and then they improve it a little bit. I say, I have a paper, I have transactions, but who cares? So the point is you must make impact, right? So for that, if you work on real problems, some of them I mentioned here, then you can make a difference. And also, especially for young people, if you don't find any literature, be happy. So don't find X, Y, Z, then your impact will be almost nil, because there are 50 other solutions that exist. Nobody will pay attention to your solution. So if there's nothing, then be happy. Then you come up with the first one. Then you get all the citations. So when people ask me, well, how did you get 145,000 citations, right? Because I send them each $1,000. That's why. so it's some people. So no, you have to be first. When you are the first, people will give you references. They follow you. So that's the key. That's the key. Because if you like, well, how I got to that is 1988. I was working on scheduling algorithms for ATM networks. Many don't know it. So, and I realized with my PhD student, there are so many scheduling algorithms from the 60s, and whatever we came up, there was no impact. I said, that's not the right thing to do. We have to find original problems and original solutions. So if you have something and n+1, good luck. Nobody will notice you. But then you can say, I have 150 papers and transactions, right? But who cares? So it's not the number. The issue is the impact. I'm not counting with the numbers of citations. During my time, we didn't have citations. I enjoy working. I did that. Now there are people, they do all these tricks. It's awful. They tricks and all that. But you know, the time shows that what you did is recognized outside. So I hope that some of you are interested in this AI direction. I'm sure you are, and especially in 6G and beyond systems. There is no way that we can ignore the AI. And I listened to a person that was really sad sometimes. You know, there are young people, they say, oh, he's a senior guy. He says that. He said 5G was a failure. I mean, only 4G was successful. The even numbers are successful. All this crap, you know. I was thinking, how the hell can you tell to these young people? Also, in the past, they said ATM failed. ATM made billions of dollars for people. I had friends, they made billions of dollars. How did it fail? These stupid people. And another guy said, oh, AI, I don't believe in AI. It will not come. So don't believe in those people. So follow your instinct and follow these things and make up your own mind. So if X, Y, Z, some famous guy comes and says, oh, I don't believe in AI, I say, oh, he said that, maybe I shouldn't believe that. That's wrong, guy. So believe it or not, but I hope you will believe me. If not, it's okay. So who cares? But AI and machine learning is the way to go. But what I'm recommending you is that's very difficult for the human mind. Reset your brains instead of taking Fuad's Mac protocol and put some AI on it. Oh, I have a paper. That's wrong. That's not good. So you say, how can I come up, starting from AI, machine learning, come up with some new protocol, for example? That's the challenge. That's not easy, but that's the challenge. So I thank you again. I hope I'm on time. Is this drinkable, this water? Thank you.
We do have time for questions.
Should stand up first. Well, thank you, Ian, for the great talk, presentation, and thank you for the last advice. I think it's very, very useful. And well, my question is regarding your talk about explainable AI. So what is your opinion about the AI? What will we become in the next maybe 5 to 10 years? Because as you said before in the talk, maybe we can come up with a theorem or a proposition from a specific AI algorithm. But now the things are getting complex and complex and even more complex. And so what do you think about your opinion on explainable AI?
So this is really my hope. The new generation, all these new coming new generations will come up with the science portion of the AI. Because the people who develop these AI solutions are mostly from computer science. And, there's also a known fact and also very upsetting for computer science people, physics, chemistry, math people, they say computer science is not a science. So because there are a lot of heuristics. In the meantime, of course, there are, many laws and all that. I mean, theorems in computer science too. But so AI is not purely heuristic. That's the problem. Like I wouldn't use AI solutions for my airplanes or rockets purely because I don't trust 100%. So that's why the new generation needs to come up again, reset the minds. That's why I say new generation, because they are new, fresh brains, and come up with some really theories and science portion of the AI. And apparently Jan LeCun mentioned that he wants to start a new AI direction. I hope that's the thing what he wants to do. I'm not sure, but so that's my hope. Like, for example, I'm interested, I'm from communication background, so I would love to have some information theory developed framework for this AI machine learning area, So really basics, fundamentals, like starting from Bayesian theorem, for example, Bayesian, right? It's all if, then, etc. These Bayesian theorems. So come up with some, slowly, right? We cannot solve everything in very fast, but that's my hope, really. Because as long as it doesn't come out of the heuristic part, and all these mission critical cases will not use AI. Like, for example, the utility companies, right? Like these electrical, etc. They need 100% reliability. They cannot assume, oh, there is AI intelligence there, but then, oops, we made a mistake because 1% was a mistake and it hit the entire city of Santa Rita, for example. So that's why we need to come up with really, work with also math people and all their physics. Nowadays, meaning the last many years, 15 years, people should really work together, different disciplines, cross-disciplinary research. You cannot just be in the corner and develop your own protocols or algorithms, because you can learn from each other. I learned from biology people. I was talking about it yesterday. I did some molecular communication. I hated biology in high school. But then I found biology people. I worked with them. I learned a lot of things. And they learned from me because we speak different languages, right? Not Portuguese, English, but the different languages. So you learn from each other, be patient, but it helps enormous. That's why I'm saying that if you work with, math, physics, like these people, and from engineers and these computer science people, you can come up with fantastic solutions. That's my advice to you. One more question. Yeah. Right.
So great. Thanks for so many provocative thoughts. When you mention AI native, you have a great point that is not having it as an add-on. But in many of the use cases that you have presented, you were still using the framework that we know of, layers, MAC, PHY, and all the traditional problems.
Good.
One related AI approach is this AI synthesizing the full networks, like a
Bravo.
true AI native that you think AI, if you had to solve the problem of getting information A to B, how would you do it? From the design of the antennas to the protocol layers to the modulation, all the way for this problem. Do you think this is something that could happen?
No, this is excellent point, okay? So really fantastic, because that's what my objective is, to give you to convergence to the AI native base. That doesn't mean we'll use the same protocol layers, the same solutions. But what I try to explain to you is that so that audience in communications can understand how these individual layers work. So I need to put a couple more slides how they should be integrated. So I didn't put that, but that's the objective. And because of that's very important. So I don't believe that we'll continue to do the same thing, physical layer network, etc. So we will come up with something new. And I don't want to reveal everything, so I have to keep certain things for myself. And so that's a very good point, actually. So I'm not advocating these 4 or 5 layers, whatever TCP IP layers. And I'm just explaining you AI is needed, how we can use for these, the way that we are doing these physical layer, etc. But the objective is try to get rid of that, convert to AI-based solutions. Very good point. Thank you for reminding me. Maybe I should put 1 or 2 just to give you the ideas, but very good. Thank you.
Hello. So connecting to what Christian just said, then I start asking myself whether we are actually prepared on the 6G cycle for this vision. Let me explain why. The way we traditionally design the protocols in, for example, 3GPP, you already by design divide in work groups that are looking to specific slice or part of the network. What you're describing here is a vision that is, I would say, walks towards like layerless. So it's cross-layer by design and everything like that. Do you think that we will be able to make this concrete already in 6G? Because the way I see 6G in terms of standardization, the way they discuss AI, it's more like evolution, what they're doing, release 1819, then comes Oran Lines, brings the on top AI layer. We are not walking towards this in 6G.
No way. Very good point. I love your questions, guys. Very fantastic. I really enjoy it. Really. I love intelligent people, really. So let me explain here. First of all, in one of the first slides, I showed the 6G key technologies. That's the way we are. Also in 3GPP, they are still talking about those. And also add on, as you said, So the things that I'm talking to you is, it will be like 6G beyond, meaning 6.5 or 7G. So in other words, it's always like that. So we say 6G, but like, let's go back to the 3G. So when we are talking about 3G, so we had let's go back to 4G. That's better. So 4G, so we were like 60% of 4G concepts. And then immediately the mobile operators started to market it. 4G is here, 4G. Everybody's using 4G, but it was not real 4G. Same thing with 5G. It's not real 5G. I remember 10 years ago, I wrote a paper on 5G. Many of these objectives were not realized, but a certain part, 60% are realized. They say, okay, 5G, they make money. 80% of humans don't understand what the hell is the 5G. They don't see the difference. They use it. So now 6G the same, but I can assure you the next 2 years, it will come out with mobile operators, but it will not be 6G, like 60% of 6G objectives. So the things that I mentioned to you is mostly beyond 6G, actually real 6G AI. But then let's move it to the 7G. So like AI native. So this is mostly like 5 years down the road, and that will be more 7G. Because don't forget it, let me add, because in ITU, I told you, I work for them today. I have a webinar with them after this. So there is a group, they are looking on the AI ML native things, and there is 3GPP and then 6G activities and metaverse. So they're all working separately, right? So metaverse will be part of 7G, for example, but some parts will be used in 6G. So it's all mixed match there.
Do you still think it will be, for this vision to become concrete, that 3GPP is prepared to
think so.
change things the way they do the standards, because it doesn't seem that they seem to be replicating the same model, right?
You know, we have a webinar series also in ITU since 3 years, 4 years, AI native webinars. So ITU is prepared. And I'm not sure, I'm sure they're also prepared that some of these things are also discussed there. So it's not like I'm giving you some crazy things that, you know, so these are all realistic objectives, you know. So, and you know, the thing is, this type of keynote should open up your mind so that you will be one of the first ones. If 3 years later you start to work on it, it's too late. Late meaning, you know, many people took the first steps, right? So that's what he said is, if you come up with some new architecture, protocol architecture with AI native based, you will be one of the first ones. People will follow you.
Thank you, Ian.
Sure.
Amazing presentation.
Thank you.
I have a curiosity. You mentioned a little bit of green AI. What does it mean in practice?
Green AI
because
meaning, look,
yes, let me complement.
Oh,
Because
sorry.
you know, the GPUs are consuming a lot of energy. In 6G, companies are proposing this energy efficiency approach in the UE side, in the network side. But in practice, using GPUs in both entities, it could be a challenge. So maybe this green AI is an interesting topic to focus.
It is.
And a complementary comment, what was asked before. What do you believe that, what should be the contribution of society on the discussion of this, the impact of AML in standardization? Because the impact is not only the technical aspect, it's only the economical aspect, the societal aspect. So I guess that's an important issue to consider if these kind of solutions can be introduced in the specification. So I'm asking you this just to maybe promote, to get your insights about it.
Okay, so first question is about green AI is really, you know, remember green communications, green networking started some years ago. So with all these, like, you know, the base stations are using diesel fuels and all that. So they try to, you know, keep the air clean and also, you know, energy efficiency. With green AI meaning, so AI techniques need a lot of energy, as you mentioned, right? To run these big algorithms and even offline, that's too cumbersome and energy consuming. So kind of, can we create some solutions which are less energy consuming? And that's why we call it green AI. So that's kind of like making these AI models simpler. Can we create synthetic data, which is like, you know, meta learning, very simple data, and then learning from that, cover huge billions, trillions of data, right? So that's the objective I'm trying to mention. About the societal impact, so it's, don't forget, you are working for a company, right? It's all about money. So yeah, it's all about money. I mentioned that GDP, trillions of dollars. So they're all interested in money. And also the humans love all these use cases, new apps. Don't forget it. All these kids, they have all these games, and it's unbelievable how much they are using these wireless, you know, mobile phones. So and the mobile operators will make money. So that's their advantage. But let's talk about from the societal impact, that will be huge. honestly. I mean, there are so many things like, I was in Abu Dhabi first time, although in America we have those driverless cars. So I took one. There was an Indian guy sitting, but he was not touching anything. So he drove me to, 30 miles to a place. So, and then we had a pilotless Formula One race. The Technology Innovation Institute, we have a group working on these driverless cars. And so we became number 2. And although we started like 4 years ago. And but what is the advantage of it? So I was thinking, these big sheikhs made investments in that. Is it for fun? But I learned that, for example, there are all these sensors for the driverless cars. Like, for example, our kids, when they are young, they are insecure when they learn, right? You can equip all these cars with these additional sensors. They can help the kids or these insecure drivers, for example, or many other sensors around. They communicate car to car. So these are all part of all these things. What I'm telling you, putting more intelligence into the machines that can help humans having more secure, safe, and comfortable lives. That's what I'm thinking.
I thank Professor Yan for the presentations and for the discussions. Thank you very much.
Thank you very much.